So we'll start soon.
So good morning, everyone. Thank you for joining me again. So let's start with news. So this came out 10 days ago. The Tamil Nadu Public Service or Public Department comes under a ransomware attack. Sensitive files were encrypted. As I told you, once you encrypt something with a strong key, there is no way to actually decrypt anything without the actual key. They demanded payment in cryptocurrency, as is usually the case. And good news or bad news is we were running old operating systems which are out of date. If you're up to date on Windows operating system releases, you know that Windows 7 is kind of an old OS. So, it's not far away. Attacks are not far away. And again, cybersecurity is in demand. Professionals will be needed to counter these type of attacks. And also remember, a ransomware attack is like the final stage of the attack. The criminals had to have got into the computer, stayed within the network for a long time. And once they have had the master access, only then the encryption takes place. So even while the criminals are on your network, you should be able to detect them. I don't think that was the case here. So it was interesting to read these. Okay. So let's go to our next section. Involves computer architecture. Okay. So how many of you have really opened your CPU, inspected your motherboard, reassembled or assembled your computer? Anybody? Okay. So in case you did not have the option, when you get it, please open your computer and try to see what's in there. So just to give you a basic idea of how it's all laid out, because if you're really looking to be a cybersecurity professional or a researcher, you must have an in-depth knowledge of how a computer works, how memory works, how your file systems work. And if you go really deep down, you might also need to know assembly language. So I'm just going to give you an introduction to all these things, operating systems, hardware, to give you an idea of where you need to design security controls around. Okay. So if you can see my screen, I've given you a basic layout of how a motherboard essentially is laid out. So a motherboard is the entire chip you see within your your computer PC box that you have. So on your left, you see your actual core, that's your CPU. CPU does all the computing, and it's connected to what's called a RAM. So you might remember what's RAM, right? It's random access memory. When you get your mobile phones, you usually, are you guys able to see my screen?
Yes, sir.
Okay. So when you go to your mobile phones, you will typically ask, what's the CPU? It's like Snapdragon. You'll ask what the memory is like, right? So similarly, in any computing platform, you will have what's a CPU, that's your processor, and you will have what's your memory. Primary memory is called the RAM. So what is special about RAM, right? RAM means random access memory. It allows you to access memory, in a random way. You can lay out information in memory in random places, and through addressing, the CPU will be able to access those bits of information. So the RAM is supposed to be located really close to the CPU, because the CPU, while it does computing, it has to be able to retrieve information from the RAM. And once you power off your computer, the information in the RAM will disappear. So RAM is also known as volatile memory. This is important when you do like computer forensics or any kind of advanced troubleshooting, right? Because if you find a computer that is essentially attacked, first thing, you don't go and power it off, okay? You need to be able to fetch the information that's currently sitting in the memory. It might be malware, you might have sensitive information that is being currently under process by the attacker. So you need to be able to dump all that information out. So when a computer is under attack, you don't power it off, you disconnect it from the network. And essentially, there are tools that can create a dump of the RAM for you, okay? So the CPU and the RAM is connected by chipsets, okay? Chipsets are companion processors, essentially, that will act as a hub, like when you are in a major junction, right? There are traffic signals that will govern how traffic flows. So chipsets allow that kind of information flow between your CPU and different peripherals. So in this case, you have two chipsets in the motherboard. One is called a northern bridge. The other one is called a southern bridge, okay? So the northern bridge peripherals are typically what's really close to the CPU and has really fast access to the CPU. So if you look on the right side of my screen, you will have the northern bridge here, a southern bridge, different manufacturers kind of integrated into different ways, but this is just to give you an idea. Okay, so if you really need fast access, you connect your peripherals to your northern bridge. Okay, so you might have latest motherboards have PCI slots. Those are extensions that allow you to connect, say, for example, your Wi-Fi adapter or your graphics card, for example, right? So PCI slots are used for it. And if you find something that's connected to a northern bridge, that'll be an ideal place to place your graphics processors, okay? And your display ports as well. So they'll have faster access to the CPU. So there are other peripherals that are connected to your motherboard, right? So you have your hard disk, you might have your audio connectors, again, your Ethernet ports, which is your internet ports, USB ports, for example. So all the other peripherals, which are kind of critical, but they don't have to be near to the CPU as such, like your memory. They are connected using a Southern Bridge chipset. So in Intel process, Intel and AMD are two major manufacturers of CPUs. So in Intel, they define it as a platform controller hub. So you have your other peripherals connected to your Southern Bridge. So the Northern Bridge and Southern Bridge, they are connected by what's called a direct memory interface. So as you can see, the Northern Bridge has direct access to your CPUs, directly connected through the bus. But the Southern Bridge, it has to go through the Northern Bridge. It doesn't have direct access to your CPU. Okay. Okay. So within a processor, there are multiple things, right? If you have seen a physical processor, it's typically like a golden chip. Within your processors, you have what's called cores. If you know about the Intel releases, you'll see dual core to duo releases, and they'll mention quad core processors, for example. So what that means is a single CPU socket, that's a CPU chip, will have multiple physical cores in them. So each core is able to perform independent processing. So every core can process one thread. Okay, one thread, I'll talk to you about it. So a thread is a subsegment of a process. So it's a small part of a process. So each core is a physical component within a processor that's able to independently perform calculations. Okay, you might have multiple CPU sockets in case of bigger systems like servers. In your desktop PCs, you might have a single CPU socket. Within that socket, you'll be placing an Intel like quad core processor, right? It has 4 cores. And the cores will talk to what's called registers. Now, we talked about what's random access memory, like that is located totally outside of the CPU. CPU registers are located within the cores itself, and it's quickly able to hold information. Like when you do multiplication or division, for example, right? You have to carry over a number, and you have to keep it separately. Similarly, CPU registers, there are different types. They are used to store, transfer, and process instructions for the CPU, give instructions to the CPU. So where can I see this? So if you look at any executable and you like disassemble it, I'm using a software called IDA. IDA is a disassembler, and I'm disassembling an executable. Like I have a Python software in my CPU, in my computer. So I'm disassembling it. Let me see. So disassembler will break down high-level language into lower-level assembly codes. Okay. So at the lower level, everything is a simple instruction. Okay. So when I see, move EAX, RCX, RAX, so these might be complex instructions in Python language, like very high level, like loop, for loop, you have your addition and subtraction. But when you go down to your mission level, it's usually, moving things between registers. And there will be simple computations. CPU will be making, adding or subtracting will be all, there are very simple instructions that CPU will execute, but remaining everything else will work around the registers. Like when it does certain calculations, it might move information into different registers, like move, call, push, okay, and jump. So the registers will hold specific values, or it might hold specific addresses that are, memory addresses. So it might load a value from your memory, it might jump to another location in memory, it might retrieve that value, or it might directly contain addresses for that memory, different things. But at the bottom level, you'll see a lot of things moving between registers like EAX, RCX, CS. So all these are registers. Okay. So next to registers, you have what's called cache. A cache is also a type of volatile memory, okay? But they're located very close to a CPU. And there are complex algorithms that drive what should exist in a cache. But it does what's called predictive fetching, right? So it kind of likely knows the algorithms that govern the cache will have an idea of what the CPU might next execute, and will have that information in that cache available. So there are three levels of caches. L1 cache is what's closest to the CPU. L2 cache is the next level. And usually L3 caches are kind of shared between all the cores. And then you have your RAM. So there are so many components in between your CPU and RAM that are used to process information that is stored temporarily. Okay. So I talked about registers, right? So depending on your processors, you might have different registers. What I'm showing you is a 32-bit operating system. We'll talk about it. So you'll have a general purpose register, you have a flags register, and you have an instruction pointer register. From a security perspective, knowing these registers is important. I'll show you how an attacker can manipulate these registers. Okay. So there, I've shown you different, just displaying you different functions of these registers, but we'll just look at three registers. Okay. Just keep it in mind. So one is what's called the stack pointer register. Second one is called the base pointer register. And the third one is the instruction pointer or the instruction register. Okay, so I talked about saying, I told you that, depending on different processor types, right? So there are two different types of processors, at a high level. So there's what's called a 32-bit processor, and then there's called 64-bit processors. Okay. So what it means is how many bits can my processor address at any given time. Okay. So when I talked about buses here, right? So 16 bits, for example, 32-bit processor, 32 bits can traverse these buses simultaneously. And your memory will also be having addresses containing 64 bits. Registers will also have 32-bit or 64-bit addressing. So they'll be able to store 32 bits at a time or 64 bits at a time. Okay. So I hope you know how bits and bytes are turned. So 8 bits from 1 byte, and again 1024 bytes from 1 kilobytes. Then you have megabytes, gigabytes, terabytes, petabytes, exabytes. Where do I see what my system is capable of processing? So if I go into system information for my computer, it's called sysinfo, shows me what my computer is. It's an x64 based PC. So it's capable of processing 64-bit information. Any questions so far? Okay. So you just got to know you can run 32-bit operating systems or applications on 64-bit processors, but you cannot do it vice versa. You cannot run a 64-bit operating system on a 32-bit processor. Okay, because an operating system has to function on top of your hardware, right? If an operating system gives you a 64-bit instruction, your processor should be able to process the 64-bit information. Okay. So next, we'll go to RAM, random access memory. Memory is usually addressed in bytes. Okay. So I talked to you about 32-bit addressing, 64-bit addressing. So when I say 32-bit addressing, the CPU can access 2 to the power 32 locations in memory. Okay. So I showed you what's 4-bit addressing looks like here. So with 4 bits, you can see how many possible combinations you can display, right? So with 4 bits, I can access 16 cells of memory. So similarly, if I have a 32-bit addressing scheme, what is the maximum amount of memory I can access? Right? Usually you have 32-bit processors here. So that means there is a limit to the amount of memory I can have in a 32-bit processing or 32-bit PC. So that's limited to 4 GB. Okay. So if you have a 32-bit operating system or processor, you can only access 4 gigabytes of memory. So that's the limit, because that's the amount of addresses I can form with the 32-bit address. Any questions? Okay. So anybody knows what's the difference between a RAM and a ROM? So RAM is random access memory. ROM is read-only memory. Anybody? Okay. So random access memory, you can write and read instructions, right? So it can be done on the go. So with read-only memory, when the manufacturer manufactures the chip, they typically write code directly on the chip, and you only have the ability to read instructions from the chip. Okay, it's not very addressable, and the operating system cannot directly interface with the ROM and read or write. There are typically ways to actually write information. There is, you can flash the UV light. There is EEPROM where you can use electrical signals to modify information that's written on a ROM chip. So it's not that easily accessible as a RAM. So we talked about memory. Memory addressing, and I want to talk about what's called a stack, okay? When you write a program and that program gets loaded or initialized in memory, it gets allocated in the following ways, okay? So first thing that gets allocated is what's called a stack. A stack is like a data structure, okay? So that will store all the values that you initialize in a program, okay? So below that, you have some unused memory where it kind of acts as a buffer. And you have what's called a heap. Heap is used to dynamically allocate memory during the runtime of the program, okay? And you'll have initialized, uninitialized memory, and you have your program code. So when you call an executable or you call a thread, this is how your memory gets allocated, okay? So going to specifically what the stack means, okay? When you call a function, right? When you write a C program, you'll call a main function, for example. And when you write an add or subtract programs, you'll initialize two variables, correct? So you'll int A, int B, then you'll call sum of A, comma B, then you'll have a return function. So you'll write a lot of things within a given function. So every function will get allocated in a stack. It'll reserve certain bytes of memory, okay? I've shown you here, for example, a function that will have our arguments will get allocated like in a reverse order. So once you initialize a function, you'll have certain arguments to the function. So it gets allocated from higher memory to lower memory addresses within a stack, okay? And then you'll have what's called a return address. A return address is where the program should return to once the function is completed. Then you have what's called your pointers, okay? So pointers is again what's called, look, it's pointed to in your registers. So I told you, remember these things, right? You have a stack pointer register, you have your base pointer register. So these registers will hold information that's related to the addresses here, okay? So the base pointer will hold the address for the base of your stack. The stack pointer will hold address to your top of your stack. So you see how the registers are used to hold information once your program gets allocated memory, okay? So the stack always goes from higher memory to lower memory addresses. So once you add information like how you stack your plates, right? So once you stack your variables, once you stack your arguments, your stack pointer will start to grow to lower memory addresses, okay? So why I'm telling all this is the stack is vulnerable to what's called a buffer overflow attack. So when I told you, when you initialize a function within your code, within your C program, it allocates a certain bytes of memory within your stack. If you do not govern the boundaries of those variables correctly, you can potentially overwrite information that's located next to what the stack stores, okay? For example, here I've showed you argument 1, argument 2, argument n, correct? If you do not govern the boundary of one argument, and if you manage to overwrite the next argument, the CPU might process information without knowing what the actual information is, okay? The CPU doesn't know whether it is the valid value or it's a malicious value or whether we have done something inadvertently. So it just processes information as it stores in the stack. If you manage to overwrite information in the neighborhood, you can potentially execute malicious code. So attackers typically abuse the stack to execute what's called a buffer overflow attack. Okay. I'll show you a simple example. So I have a C program here. Can everybody see my screen, the program? Okay. So this is the program I have. I've been asked, like from my managers, for example, hey, write a program that takes a password. And if the password is correct, do some privileged stuff, right? So important transactions, executing system instructions, for example. So it's very simple in program, right? So here, okay, I developed this code. I developed a C program. I initialize a variable, 16 characters for the password, and I initialize an integer and just make it 0. Now I ask a question, right? What's your secret password? And here is where it gets, security-wise interesting. I use what's called a gets function. So a gets function typically takes whatever information you put in. It doesn't look for those boundaries, and it will write it to the buffer that I showed you, okay? So I get that information, and I compare the string that I got with a secret password. Let's say that's my password. It's very weak. I'm just comparing it. And if it doesn't match, I'll print you fail, okay? Else, I say, this is the correct password, and I change this string, or this integer from 0 to 1. Okay, that means I passed. Okay, so if I pass the next line of code, I'm doing some privileged stuff here, right? It can be an important transaction, some system level processing. So this seems like a simple C program, right? So how do I exploit this? So I remember I told you this function does not check for limits. So when I initialize these variables here, what happens is I initialize 16 bytes for characters, right? For my input password. And I initialize an integer pass check with the value 0. So those are located one against the other in the neighborhood, right? Next to each other in the stack, okay? So when I get the password, when I compile my C program and I run it, when I get my password, I have the potential to overwrite this integer because I'm using a function that does not implement boundary checks. Okay. Here, what I check here is if pass check is a non-zero value. Okay. If it's a non-zero value, it's going to do privileged stuff here. If I override this pass check integer, pass check variable, I can potentially do privileged stuff. Let's see how it goes. GCC is a C compiler. I'm just using an argument not to implement stack protections. Operating systems these days have stack protections in place. I'm compiling the program. So it immediately says, right? So the gets function is dangerous, should not be used. So it's file, sorry. Okay, so I'm running the program. So it asks, what's the secret password? Okay. Again, if my password is a string that I put in, then it should potentially let me in. I'm putting the correct password. It says correct password during privileged stuff. Okay. I put in a wrong password, right? It says you failed. So it works correctly at a high level. So let me try to overflow the buffer. Okay, let me try to override the neighbor variable. Okay, asks what the secret password. Okay, it's a really long string. I'm trying to potentially overwrite the integer check here. I'm trying to make it non-zero so that when it does this check over here, it will find that it's a non-zero variable and it will try to do privileged stuff. It says you fail, but it correctly entered into the privileged part of my code. Okay. So when you write a program, make sure you have or you use functions that implement boundary checks within your stack. Any questions so far? Okay. So there are other ways an attacker can potentially overflow your stack. I told you there is what's called a return address, right? So a return address, you might have sub-functions within a program. A return address will correctly take you to the next function that needs to be executed within your program. So what if an attacker can potentially change this return address to an address that contains malicious code? That is possible. Okay, it is a bit complex, but it's still possible. Okay, and if he's able to change the return address, and if he's able to exploit this instruction pointer, now the instruction pointer contains the address of the next instruction to be executed. Okay, so if he's changed the return address, and if he changes the instruction pointer in a way that it can go to his code and execute it, you will potentially have an attack taking place. And that's all this is taking place inside your memory. It's not even touching your hard disk. Okay. So input validation, all it means. Whenever you get an input from your user, make sure you validate the input. For example, in my program over here, I should have, even though I shouldn't have used something like gets, I should have checked whether, the input is a 16-character max password, right? I should have checked whether there are certain strings that might execute code within the input that I get. So all these validation checks will really help in making your program, the program that you develop, a much safer place. If you deploy a piece of code into production, and then somebody finds a vulnerability, to go back and fix the program is going to be a really expensive exercise, both for you and the organization that you work for. So every time you get an input from a user or any application, anything that traverses different things, like from your web server to a database, always make sure you have validated what's being gotten as an input. Otherwise, you will be vulnerable to these type of attacks. Any questions so far? This is a bit of a complex topic, but I attempted it to show to you, because this is, if you Google what's the top 25 vulnerabilities, a buffer or overflow attack is almost always like number one. Okay, so we understood a bit about motherboard, CPU, memory pieces of hardware. Now let's go to operating systems. So what are operating systems? So operating systems are system software that executes code on your hardware. So it has a variety of functions. It governs processing, it governs your peripherals. So everything goes through your operating system. The hardware itself doesn't have the ability to do anything. So you must have an operating system on top to be able to process things, to govern things, and to manage things. Okay. So an important part of the operating system is what's called a kernel. A kernel is the core of the operating system. And that's what gets loaded the first time you power on the computer. And it's always resident in memory while the computer is powered on. And it manages all the resources. Okay, it manages memory, time, and the tasks, how information goes back and forth between processor and your memory, from the processor to the memory, to the hard disk, from the to all the peripherals. So it kind of governs all these things. Okay, and a kernel runs in what's called a privileged mode. Okay, as a user, my applications will not have direct access to the kernel. Okay, it runs in what's called user mode. Whatever applications I have on my computer, it typically runs in a user mode. The reason they have developed this system is, there's a principle called protection rings around OS. Okay, this is for security. A kernel has access to all the resources within your computer. Okay, that includes your printer, your keyboard, your mouse, monitors, your USB drives. So anything that has high privilege access to device driver or your devices or your processes within your, components within your motherboard will need a higher privilege or a higher level of protection. So Intel, they developed these kind of protection rings. You have what's called ring 0, ring 1, ring 2, ring 3. So ring 0 is what the kernel runs in. It's a logical setup. It's not like physically you can see the rings. So it's a logical setup. So the kernel runs in a ring 0, which is high privilege. Then you have your device drivers. Device drivers are pieces of code that interact between your OS and your actual hardware. Like when you plug in your USB, you typically have a pop-up that says, please wait while we install your drivers. So anything that has access to peripherals, your devices, or components on your computer will need high privileges, and therefore they don't exactly run at ring 0, but they run in one level down. So they typically occupy ring 1 and ring 2. And then you have applications at ring 3. So these are the privilege levels. Anytime an application has to talk to the kernel, it has to go through a reference monitor. This is a line over here, but there is a governor in the middle that kind of says, oh, okay, do you have access to the kernel? Okay, then it will allow you to actually access the kernel. So because device drivers, they require very high privileges, major operating systems like Microsoft requires that kernel mode drivers are digitally signed. So we talked about what digital signature is, correct? It ensures the integrity of your code or your authenticity of your information. Okay. You have to submit whatever drivers you develop to Microsoft. They will validate it and they will sign the code for you. And only then you will be able to run a code that requires kernel mode access. Okay. They do not run Microsoft Windows. It doesn't run any device driver codes that require kernel access without Microsoft signing the code. So they actually put a digital signature to ensure the integrity and the authentication of your code. So that's how kernel is protected these days. Any questions? Okay. So let's understand boot process. What happens when you power on your system? Okay. Okay. The first phase, when you push the power button, what happens is the CPU will access what's called a ROM. Okay, it's a very small chip. and it will test all your peripherals, your motherboard functions. You will typically hear a beep when you power on your system, right? So that's what it is. It tests all your components, make sure all the hardware is functioning. Okay. At that point, if it fails, it doesn't go any further, right? You'll hear like 3 beeps, 4 beeps, depends on your motherboard. You might hear different types of beeps. So it just activates a small piece of ROM and it will test all your peripherals. That's called a post test. Post is called power on self test. Okay. So once it tests everything, once the power on self test completes, it activates what's called a BIOS. Okay. BIOS is another piece of ROM. So you might have a screen that flashes, right? Press F2 to enter BIOS or press F12 to enter BIOS, depending on different systems. You might be asked to press different keys. You will have access to the BIOS if you do that. So once you do that, you will be able to see what the BIOS has for you. It's typically a blue screen on Windows. The BIOS will have basic information about whatever hardware is connected and your system time. You might be able to change what you boot from. For example, you might want to boot from a CD, you might want to boot from a USB device, you might want to boot from regularly your hard disk. So all this information is given within your BIOS. Okay. So once the BIOS is activated and it's able to ascertain what it's got and it's able to determine what you want to boot from, like your CD or your hard disk, it looks for what's called the master boot record. Okay, the master boot record is located in your hard disk. Okay, so it's located in what's called the sector 0. We'll talk about it. So the master boot record, it holds information about partitions, file systems, and it also has what's called the Bootstrap Loader code. Okay, so where does it exist? I can see that. So I use a software called WinHex, and I loaded my drive over here. Okay. So in Windows, there is what's called a $boot file. So here it is. The first 512 bytes, the first sector, contains what's called the master boot record. The code is unintelligible, but the offset, if you see, it's 0. So this is where my master boot record contains. So it has information about my partitions in case if you know what Ntfs is. So it says I have an Ntfs partition, Ntfs file system, and the remaining is information about how to boot my kernel. Okay. So it activates what's called a Bootstrap Loader. The Bootstrap Loader activates what's called an early kernel. That's called, it's a smaller part of my kernel that's used to initialize my memory, like my RAM. Okay. Once that's done, it will transition to the full core initialization. It will load the entire kernel. I talked about what the kernel is, right? It's core of my operating system. It will load everything into memory and it can execute from there. Any questions about how the system boots? Okay. So I just want to talk about the BIOS a little bit. BIOS is an old form. The newer version is called a UFI, like Unified Extensible Firmware Interface. So BIOS is again stored on an EEPROM. It's again a ROM chip that's on your computer. I think I showed it to you over here. So if you look at my picture here, I would have shown you the BIOS. It's again a ROM chip in this part, in this picture. I think it's over here. So Where are we now? Okay. With UFI, it's stored in an initialization file called .efi file. The limitation with the BIOS is it can only support 2.2 terabytes of hard disk. Okay, with UFI, of course, it can support drives up to 9 zettabytes. The important part about UFI booting mode is it offers an option called secure boot, which prevents the computer from booting from an unauthorized or unsigned applications. I talked to you about what signed and unsigned applications are, right? So typically you have somebody verifying your authenticity of your code, the integrity of your code. Any questions so far? Okay, let me briefly talk about a hard drive structure. If you might have seen a magnetic drive, what's inside, you have what's called your head. The head is what tracks the information. And you have a platter. A platter is what you write your information on. And you have what's called your spindle. Your spindle is your center section of a hard disk. It allows you to spin your hard disk. The spin platter, sorry. So within your hard drive, you have what's called a track, sector, and a cluster. Tracks are concentric circles around the spindle on either side of a platter. So if you look at it over here, you'll have a head that's on top. You'll have a head that's on the bottom as well. You'll have multiple platters, and you'll have heads on both sides of the platters. So a track is logically a single concentric circle on each side of a platter. Okay, so within each track, you have what's called a sector. Okay, so when you divide a platter into what's called sectors, you get like arcs, right? So each arc is formatted to hold certain amount, a fixed amount of data. So typically that's 512 bytes. So when I mentioned how your system boots, I told you that the BIOS will look for what's called a master boot record, and that's located at sector 0. So this is how it's addressed. So it will look for sector 0 on my hard drive. Okay. So we got to understand what a cluster is as well. So a cluster, it's a logical thing. It's not a physical aspect on your drive. So cluster is the smallest amount of disk space that can be allocated to hold a file. So it could be 4 KB in Ntfs. Depending on your size of the drive, the cluster size will vary. But it's the smallest amount of, like say, it's a box into which your file is placed. Okay. So what that means is storing small files on a file system with large clusters will waste disk space. Such wasted disk space is also called as slack space. So if you have a really large cluster defined and you're always putting like 1 KB files in them, because cluster is the smallest amount of space allocated for a file, you will waste essentially, like if you have a 4 KB cluster, you will waste 3 KBs for every 1 KB file you place. Next, let's talk about file systems. We talked about RAID, right? So when you actually create a RAID volume, you'll create what's called an uninitialized partition. Okay, so here's a screenshot. This is a software by HP. It's called Smart Storage Administrator. So when you plug in physical hard drives, the software allows you to create RAID configurations. So here I have 4 2 TB drives, right? I've created a RAID 6 over here. So it shows me what the capacity and all is. So once I've done this, and if I go into my Windows Disk Manager, this is just an example. It shows 22 gigs, but ignore it. I'll be shown an unallocated partition over here. So what I can choose to do is format this partition. So formatting this partition will cause it to format in the form of a file system. A file system is a way in which files are indexed and organized within your PC or your operating system. Okay. So there are different file system types. First one is FAT32. A FAT32 was the older standard. It was used in USBs and many other operating systems until recently. FAT32 supports files of up to 4 GB in size and volumes of up to 2 TB in size. So it was compatible across operating systems. FAT32 was the kind of standard in the olden days. So this is how file systems were formatted earlier. The next partition type is Ntfs. So this is also the type of partition my system uses, Windows. It has very large partition size limit that supports very large files. Importantly, it allows me to set file permissions and allows a concept called encryption. We learned about it, right? The next file system type is Exfat. It's optimized for flash drives. You might have seen when you choose to format your USB drive, Exfat might be an option it displays because it's compatible across operating systems. For example, Windows only uses Ntfs. You cannot use an Ntfs formatted drive on a Linux system, okay? But Exfat is kind of compatible across different operating systems. But it doesn't have any overhead of like Ntfs because Ntfs has the ability to set security. It has some overhead. And it doesn't have limitations of FAT32 as well because it supports only small sizes of files and volumes of only 2 terabytes. ext4 is a Linux partitioning scheme. So Ntfs and ext4 is what you might typically encounter in your day-to-day work. And if you're using flash drives, for example, you might see them being partitioned in Exfat. Any questions so far? Okay. So if you're gone into a Windows system, for example, you might see these folders, okay? So within Windows, you have what's called C Windows. C Windows itself contains what's called the core of the operating system. As an attacker, I'm really interested to go into this folder. If I gain access to the System32 folder, that means I have admin access, okay? So any attacker will typically target us, the System32 or the Syswap64 folder. So within Linux uses what's called a slash mechanism. Slash just means root directory. I'll show you all these things. So you'll have a /bin, /boot. Everything in Linux is a file. So Windows has what's called a registry as well. But in Linux, everything is a file and everything is traversed from the root directory. Okay, when you mention slash and you mention a directory, it goes along that hierarchy. Okay, so there are different types of structures that are reserved for Linux. I'll show you these things now. Okay. So I have a Windows system running within my Windows system. Okay. So what I'm showing you is the registry. So registry typically has configuration information that's related to your operating system. It also has information about your passwords and everything. This is kind of a weakness for Windows because Linux, everything is a file and different distributions have different file structures. It's really difficult to compromise a whole Linux environment. But Windows, if you have really high privileges, if you can compromise a registry, it means you can have access to everything. You can even run what's called a fileless malware. If you can load the right information into registry, you need not write any file like any executables, viruses on your actual device. You can directly retrieve that information from registry and load it directly into your memory. Do you know who has highest privileges in Windows? Which user has highest privileges? Anybody? Anybody knows who has the highest privileges in Linux? Okay. So in Windows, it is administrator. So there is a user called administrator, and that user has the highest privileges on Windows. On your home PCs, you're typically the admin, but in an enterprise environment, you might want to disable the local administrator on a PC. It's taking a bit of time. I'll allow it to load. So let's talk about security permissions. Okay. So if I go into a Windows system, right click it, and I go into properties. For some reason, this is slow. I can assign what's called a security permission. Okay. So I have talked about this briefly in discretionary access control model, right? As a system user, you can assign what actions can be done to your folders. Okay. So here are different capabilities as far as Ntfs is concerned. So it has full control, modify, read and execute, read, write, list folder contents, and you can also go into special permissions. Okay. And I can add a permission here. Okay. So this screen has popped up. So I told you about the administrator account, right? So the administrator account is disabled on enterprise editions. It has the highest privileges in a Windows operating system. And you might have a guest user, and you can define multiple users within your Windows operating system. So I've created what's called the user one. I can create new users as well. And there is what's called groups. So different groups offer different capabilities within Windows. If you look into administrators group, you might have people in here whom you think that they might need to administer the system. They might need highest level privileges here. So you might see administrator here, but the user is currently disabled. So you see a down arrow over here, it's disabled. So that's the best practice. So going back to the folder, so I can change a permission on this folder. And I can add a user to have access to this folder. So if you have a user defined in your Windows system, let's see if this works. I had user 1 defined. Okay. And I can give that user permissions to do different things on my system. You have allow permissions and you have deny permissions. Deny is not used extensively because if you don't have a user defined within your properties, security properties, they automatically have no access. Sometimes it's used to deny access to a subset of users, but usually you control access to a folder using the allow control. So I can hit apply. Oh, I don't think I have access. But this is how you would probably do it. And besides security permissions, you have what's called a share permissions. A share permission allows you to access this folder on the network. Okay. So whenever operating system kind of checks if a user has access, it uses both the share and security permissions to decide if a person has access to the system or not. Okay, even here you have the ability to define what controls or capabilities you can have. The usual permissions are, I think, full control, change, and read. A security permission is more well-defined. A share permission is usually just these three. Any questions so far? Okay. So with Linux, I'll show you very briefly. There's a command called tree / So I told you Linux has a different set of files or file systems. So you have what's called the bin, the boot, CD-ROM, dev. You can look up these terms on the internet. You might be able to find what these are specifically used for. So Linux uses a different type of permissioning or ls-l is a command I can use to list all my files and directories and the permissions that are assigned to them. So here you have RWX, read, write, execute. D indicates whether it's a directory or a file. Okay, this is much better. And there are multiple RWXs, right? So the first RWX is for the user. The second RWX is for the group. And the third set of RWXs is for others. So typically this is how permissions are laid out in Linux. You can use chmod, that's a command you can use to modify permissions on Linux files and folders. So research all these permissions, shared permissions, security permissions, how these are assigned in different operating systems. So this will come in handy when you are learning ethical hacking or when you're designing your own applications. When you have applications, you might have to create folders. Make sure you have the correct security permissions for the users that have access to the folders that you create and the applications that you design. Any questions? All right. Thank you for joining today. I'll meet you in the next class.
Thank you, sir.
Thank you.